Okay, YouTube, this is our last video in our module on solving systems of linear equations in which we're going to confront the infinitely many solutions case. And so I guess in our last video we had confronted the idea that if we're graphing systems of linear equations, at least two equations and two variables, we'd see that they either have one solution or no solutions or infinitely many solutions. But in terms of infinitely many solutions, we see that really the two equations produce the same solution sets, or at least the lines intersect everywhere, which would mean that they really represent the same equations. So we're going to say that essentially we get a dependent system, or at least the equations in a linear system with infinitely many solutions are called dependent. So we say that if we attempt to solve such a system by substitution or addition, you will eliminate both variables, so something we saw happen with no solutions cases, but what we end up with is a true statement like 10 is 10 or 0 is 0. So different from our last case where we got all of our variables to eliminate, but we ended up with a false statement. We're going to end up with the true statement here in this case. And so we're going to look at a couple of examples. Let's just go ahead and start with example number 6 here, which is already graphed for us. Essentially, what I want you to see is that our system, this is interesting, our very first equation is given in slope-intercept form. So we can see that it's a line that has a y-intercept of -2, hits at -2, okay, easily can see that. And then we'd say that it has a slope of 3, so it rises 3 and runs 1. We could see that these are all the solution pairs to it. If we look at our second equation here, this is in standard form, but that would have been easy to graph as well. We could say, well, do this by, I guess, intercept method. If you plug in 0 for x, okay, we would have gotten a y value of, I guess, if -5y equals 10, of -2. So we would have gotten -2 for y-intercept. To plug in 0 for x, -5y equals 10. Plug in 0 for y, we get 15x equals 10. We get our x-intercept is 10/15. So in other words, I suppose that would be 2/3. And so we can see that our x-intercept is at 2/3 here. But essentially, it's the same thing. Now, the reason why, and I'll tell you why, that they give it to you, one in slope-intercept and the other one in standard form, is because if I were to argue this, what if I wrote this in standard form? Then our first equation would have looked like this, and our second equation, 15x minus 5y equals 10, what I want you all to see is that it's pretty clear to see that this first equation, if we multiply it by a 5, it just is the second equation, except for its exact opposite. We would get plus 5y minus 10. And so this would be an instance where both of these would cancel out and we would get 0 equals 0. So now, one thing that I do want to confront is that, I kind of went fast there, is how you might solve a system like this here. If we were going to solve this system algebraically, I would have encouraged us to actually use substitution first, but because we've already have y isolated here, already have an isolated variable. So what I'm going to write is a little note here. We'll use substitution, and we'll just go ahead and get started here. So since y equals 3x minus 2, what we're going to do is we're going to take that and plug it into our y on our second equation here. So what we end up with is this 15x minus 5 times our y value in terms of x, but we know that y in terms of x is this 3x minus 2 from the first equation. So let's go ahead and clean this up here. We end up with 15x minus, I suppose, 15x, and then we would get plus 10 equals 10. And so you know how they were talking about that 10 equals 10 statement thing being an always true thing? Essentially what you see here is that this is always true. And so this is a little bit different when we write our answers here, always true. We're going to write one thing. First of all, because we got an answer, this system must be consistent. We got at least one answer. And because these two lines intersect everywhere, we're going to say they are dependent upon one another. So writing our answers, how we would do this, you'll notice that they're including these little brackets down here. And this is how they've written their answers here. Essentially what we're saying is it's the set of all points x, y that are on these lines. And so because we say infinitely many solutions doesn't mean that any point works. We say infinitely many solutions means any point on these lines works. So what we're going to say is that the solutions really are the set of all ordered pairs x, y, and this bar here, we'll read it as such that, but basically such that y is always equal to 3x minus 2. And you'll notice that this over here says all ordered pairs such that 15x minus 5y equals 10. In other words, all they really did was say that, yeah, as long as they're on that line, then I suppose we'll be good here. So let's go ahead and take a look at this last system here. I notice that x is already by itself. Let's go ahead and solve this by substitution. And so what we would get is in the second equation, which is 5x minus 20y equals -40, if we were to plug in for our x value now, what we know x equals, whoops, got a little ahead of myself here, we minus 20y equals a -40, okay? then we would end up with this 4y minus 8 being our x value. And so distributing here, looks like we simplify out to be 20 y's, negative 40 constants, negative 20 y's, negative 40 constants. Combining like terms here, looks like we end up with negative 40 equals negative 40. So in this case, we're going to say that we have a consistent, dependent system. Dependent. Okay. We would say infinitely many solutions. Infinitely many solutions. We're also going to say that these equations graph the same line. In other words, have the same solution sets. And then the last thing we have to do, and this is not true with no solution, but it is very true with infinitely many solutions, we have to write our solutions kind of like we did over here in the set builder notation that says, look, it's all the points x, y, such that it has to be on one of these lines right here. So what we're going to do is we're just going to take our pick. I'm just going to grab the first equation up there, but such that x is always equal to 4y minus 8. Any of those points are going to make that true. Cheers.